Good morning, everyone. My name is Aisha. My teammates are Amruta, Francis, and Vikyat. Under the guidance of Swati Madam, we are conducting a project named as a novel solar photovoltaic fed TransZSI-DVR for power quality improvement of grid-connected PV system. As we are a team, we are a final year of BTech from Annamacharya Institute of Technology and Sciences, Rajampet. Today, we are presenting a project. Today's agenda as follows. Today's topics are objective, introduction, circuit diagram of PSI-DVR and output waveforms of PSI-DVR, ZSI-DVR and TransZSI-DVR. Here we are conducting simulation circuits on MATLAB and following comparison of THD values. We conclude with conclusion and references. The main objective of this project is to improve the power quality of on-grid photovoltaic systems by implementing a new TransZSI for improvement of power quality. In this project, a new solar PV fed dynamic voltage restorer based on TransZSI inverter is proposed to improve and enhance the power quality of on-grid photovoltaic system. As for those who don't aware of DVR, is a power electronic compensator using for injecting the desired voltage to the point of common coupling as per the voltage disturbances. Here we are concluding voltage disturbances as sag, reduction of voltage, swell, increase of voltage, and interruption. The power where the power is disrupted. The proposed DVR, in place of we have traditional VSI, ZSI, so we are implementing TransZSI in place of traditional VSI and ZSI. With the outstanding merits of buck boost converting capability, a broader wide range of voltage boost gain, lesser passive components, and lower voltage stresses. It's put forth for efficient detection and accurate voltage disturbances, mitigating and lessening the injected voltage harmonics. A hybrid vector template with maximum constant boost converter, which is known as UVT-MCT method, is proposed for TransZSI-DVR. To improve the performance of the proposed TransZSI-DVR with the help of UVT-MCT method has analyzed under sag condition, severe sag, slight sag with harmonics, swells and interruption. The comparative studies and simulation results have shown the effectiveness of the proposed TransZSI-DVR as proposed to traditional VSI, DVR and the TransZSI-DVR in the PV system has mitigated voltage, swells, interruptions. It also improved the power quality of both injected voltage into the PCC and the output of the power system. I hope this is fine. Where we have, this is helpful for the environment conditions for where the sustainable energies, the future of power is going to be on solar. So we are proudly to announce the proposed system circuit diagram. The circuit diagram as shown in the figure. As shown in the proposed TransZSI configuration, in this figure, we have DVR is connected in series to the PCC on the supply side. In this project, we have the output of the grid connected to the PV system to detect the disturbances, including sag, swell, and interruptions, and then compensate for them. The PV system compares the PV array, which is this PV array with an MPPT controller, boost converter, AC to DC, VSI, and three-phase transformer and distribution network to which the PV array is connected. In normal condition, this DVR is in standby. Once voltage sags, swells, and interruptions happen, the DVR detects them and as per the amount and duration of the voltage disturbances, and then it injects the desired voltage to the PCC. The DVR compares a PV panel battery. This is a PV panel and this is a battery energy storage system, which is used to improve the injecting power and absorbing power into the system. The proposed TransZSI-DVR with a UVT-MC-BC method controller and an LC filter to filter out the harmonics present in the system, and a three-phase injecting transformer to inject the desired voltage. When a voltage disturbance occurs on the supply side, the energy stored in the DVR provides its desired energy. The energy storage can be a DC link capacitor or a battery. Here we are using a battery energy storage system. The capacitor storage is lesser than the BSC, which is why BSC is widely used. In this work, we have integrated the PV panel and BSC is proposed for TransZSI. On one hand, solar energy lowers the battery energy restrictions. Recharging the BSC with solar power offers a convenient option for DVR. Batteries overcome the intimate corner of PV panels. These integration serves the need for addressing the issues related to the capture of energy in the PV panel and issues related to the energy consumption of the battery. There are two traditional VSIs and ZSI DVR in the traditional way. In the casual form, the performance of the comparison with the proposed TransZSI. For VSI, we have used UVT-based pulse width modulation is used. For both VSI and ZSI, TransZSI DVRs, we have used UVT-MC-BC method is applied. Therefore, there are different case scenarios of where we have comparing VSI DVR with UVT PWM method, with this pulse width modulator method, ZSI with UVT MC-BC method, and TransZSI with UVT MC-BC are carefully analyzed in this work, where VSI is widely deployed to form the interference of the grid connector for renewable energy sources. However, VSI has limitations. That's why we have used this TransZSI in place of VSI and ZSI. When it comes to VSI, we have problems related to the addressing, such as they have pointed out the lit where we have seen a shoot through is boosting the voltages, where we have only buck future in VSI and ZSI. So that these problems are encountered in TransZSI. TransZSI has shown super performance in price, voltage gain, and voltage stresses on the switches, where we have controlled each leg of the TransZSI's DVR inductors to deplete the structure of the DSI. We have seen. These are the advantages of VSI, where we have the limitations of the VSI. While using VSI, we have seen from 0.05 to 0.1, we have severe sag, and 0.15 to 0.12, we have light sag. And the period from 0.025 to 0.3, we have swell. And the period 0.35 to 0.4, we have interruptions. These interruptions and sag swells are eliminated by using DVR, which will inject the voltage, desired voltage at the point from. These are the output voltages from the period 0.05 to 0.1, which is severe sag. During this period, the VSI DVR is injecting the voltage, but in a very lesser amount. Due to the disadvantages, these have harmonics included in that. That's why we have interruptions, we can see here. These interruptions are unwanted. That's why we are using ZSI. In place of VSI, we have used ZSI. The main disadvantages of VSI is bucking capacity. We don't have boosting capacity. That's why we have used ZSI, where we have boosting capability, where bucking capability is lesser. So we next implemented TransZSI, where we have buck and boost capabilities together in a system with amazing wider ranges of voltage gain, lowering the voltage stresses, and implementing the power system efficiency, implementing more advantages than the sustainable energy sources. This is the proposed system which bug boost capabilities. This is the proposed system with bug boost capabilities, where we have used UVT MCBC method as an improve mode to control the injecting voltage at desired levels by controlling the each voltage, where we have using the voltage switches where to improve the signaling, when to stop, when to inject, and when to observe the signals. This is the proposed system, the TransZSI, implemented in a MATLAB, where we have seen the different case scenarios implementing each other, where we have compared each of the signal with the desired one, with the traditional ones. This is a pure sinusoidal form of similarity. We have used case scenarios as similar when compared to VSI, ZSI, and TransZSI to compare to analyze the picture, where we have encountered how much quantity those compared to traditional ones, the proposed ones. So we have studied THD values for TransZSI and almost on VSI and ZSI, where we have concluded that TransZSI have more superior performance capability than VSI and ZSI. Wherein during VSI for the period of severe SAG, it was showing 10.73, where we have by using ZSI, we have concluded that 10.19 reduction of almost 6 points is reduced in proposed TransZSI, which is 4.25, which is as according to IEEE standards, the maximum range, which is the minimum range, which should be the THD value should be less than 5%, where we have concluded this is the 5.14, 5.23, and 5.09, where the reduction is also seen, where 50% almost reduction is shown in here. We concluded this analysis with using these references, which is our main course suggested by the famous authors. Thank you. Thank you for listening us. Thank you. Now come to the results, where we have seen this is the results for MATLAB. This is a simulation results we are going to see. Before that, we have to open the MATLAB file, where we have seen this is the MATLAB.mat file, where we have included the frequencies values. Switching frequency is 10,000 hertz. So I am loading TransZSI, which is a proposed one. It will take some time to load the values. This is the IEEE 15 bus system with the standardized values. At bus 3, we have placed our solar plant. Before that, we have to run to see the THD values. Here it is comparing. The final results of this project. As we have seen here, this is the output waveforms of TransZSI-DVR. We are comparing with the theoretical values with the practical values. This is the supply voltage. During 0.05 to 0.1, it is severe sag, and 0.15 to 0.2, this is light sag, and 0.25 to 0.3, this is severe sag, and 0.535 to 0.4, it is interruption. We have concluded which is similar to the theoretical values. These figures represent the first half of the graph in the theoretical value. Next, this is DVR, TransZSI-DVR's output waveform, which is injecting and observing waveforms. During 0.05 to 0.1, which is severe sag, the voltage which is lesser or which is desired one will be reflected injecting from the TransZSI-DVR, and this is the light sag session, which is the required. These sag and swells are to maintain the continuity of the power supply without any interruptions. Finally, we are going to represent the output waveforms, final output waveforms, where we have seen continuity of power supply without any interruptions such as sag, swell, and any interruptions. We have maintained the continuity of power supply, though there are severe interruptions such as sag, swell, and interruptions. These are the waveforms, and now we are going to see the THD values of each period. This is the entire road signal value. Where we have 5.78% THD as a load. Now we are going to see the time period during 0.5 to 0.1. We are placing 0.5, the time period of 3, because here we have seen 3 cycles, 3 repetitive cycles. So we are trying to measure the values, THD values. Now we are going to find the THD values for the remaining ones. In overall, we have maintained the value for each period as IEEE standards of THD, which is which is less than or equal to 5%. Which is 5.78. When compared to other DVRs, TransZSI have shown 5.78 when compared to other. Thank you.